Yes, thank you. I'd like to thank the organizers for organizing this nice conference and inviting me here. It's a great pleasure to be in Mexico again and in Guanajuato. I'll talk about our results that I obtained with Tomasz Komorowski, but the problem itself arose when I was talking about our joint work with Tomasz Bojdecki and Luis Gorostisa at a conference in Poland, where I was talking there about the Rosenblatt process and our particle picture interpretation, and then we started talking with Tomasz about the possibility of this work where we thought that the Rosenblatt process or something of this kind might appear in the limit. So the problem is the following. We consider we have a certain random field, V. This is indexed by T, which is time, one-dimensional, and X is in dimension RD. And this is a random field that also takes values in RD. And consider, so only the field is V is random. And consider this differential equation. You can think about it as V is random velocity field of a certain fluid, for example, and there is a particle, massless particle in this fluid who moves there and whose velocity depends on the position where the particle is. This is xt. So this is the position of the tracer is described by this equation. And this is a popular model in hydrodynamics, and the transport in turbulence goes back to Taylor, 1923, then Kreichmann, Frisch, Falkovich, Gawęcki and Vergasola, Majda, Kramer, Monin and Jaglom. You can find this model there. The usual assumptions on this velocity field are the following. It is assumed that the random field, the V, is divergence free. That means that the fluid there is incompressibility. The fluid is incompressible. Simply means that the gradient over V is identically equal to 0. It's a partial derivative with respect to Sj of V, the J's coordinate. If you sum them up, then it's 0. It is also assumed that the random field is stationary with respect to both time and space. So it's the distribution is invariant with respect to translations of the space and time. And V is isotropic, that is the distribution is invariant with respect to rotations. The properties of incompressibility and stationarity imply that the process of velocity of where the tracer is, so look at the velocity of the tracer, is stationary. And this is an important property for us. And what we'll be looking at, again, not a new problem because people considered it before, but assume that V is above and consider the case where this velocity is scaled by epsilon that converges to 0. So this very small velocity, but we look at the process at long time scales. So time is also scaled by here negative power of epsilon. And the question is, what is delta and what kinds of limits one can obtain. So first I'll describe some known results, some of them quite old. Here I wrote again the equation that can be under here with this scaling. It can be written in this way. We assume that the particle starts at 0. This is not very restrictive. So if you look at this and consider the theorem of Port and Stone, then you immediately see that if the limit exists, then it would have, since this is stationary, so the limit would have stationary increments. And what is known? First, in the works of Kazminski and Kesten Papanikolaou, you can find the theorem that if V is as above, that is divergence-free, stationary, isotropic, and sufficiently strongly mixing in T, in time, then there is diffusive scaling, and the process of the tracer motion converges in law to a Gaussian process which has independent increments. It has certain dependence between the coordinates, but it has independent increments. And it can be written the covariance matrix of the one-dimensional distribution is this dj prime that involves the covariance of the random field at times t and 0. And so at least this integral has to be finite. This is known as Taylor-Kubo formula. I'm not sure if I mentioned, but V is assumed to have mean 0 here. And of particular importance in this theory are the random fields whose energy spectrum satisfies power law. That is, the covariance has the following form. Here, first there's stationarity, so this doesn't depend on T prime and X prime. And this power law, so there is certain, well, you need certain cutoff, so AK is a cutoff function that has compact support, but it's needed so that this V is smooth enough so that one can write the equation and solution. And power law, that is here the power of, there is a power of K, certain power of K in the spectrum, KD minus 1, but also in this E0 you've got something that behaves as a power of K. And the part with time also has got, there's exponential here. Time and a certain power of K. These fields are important. And there is term gamma JJ prime, which is written here. This term is responsible for the field being divergence-free. It has to appear there if the field is to be divergence-free. And this form of covariance is important because in the theory, because it is claimed by Kolmogorov and Obukov that the Eulerian velocity field of a fully turbulent flow of a fluid can be described by random fields of this form. So in particular, if you take V that has this covariance, and then those djj prime that appear in this theorem and in the Taylor-Kubo formula are finite if and only if this integral is finite, which means that the terms alpha plus beta is smaller than 1. Let me recall again what alphas and betas were. Betas were the powers near RT, and alpha here is in the spectrum k to d minus 1 times 2 alpha minus 1. And there was another result of Fanyang and Komorowski, who showed an example of a random velocity field that in this setting would give super diffusive scaling, and the limit is no longer has independent increments, but is a fractional Brownian motion. Namely, each of the coordinates is a fractional Brownian motion. Again, there's some dependence between the coordinates. So here is this theorem stated. So they constructed a Gaussian random field with mean 0 and covariance, as I have shown you. Of course, now alpha is smaller than 1. This is so that the field is well defined. And alpha plus beta greater than 1, so the Taylor-Kubo formula no longer holds. Then this is the scaling. Delta time is scaled with delta as this, and they obtain in the limit in law as epsilon tends to 0 a fractional Brownian motion, the dimension fractional Brownian motion. Possible values of parameters are between 1/2 and 1. And in their proof, they used moment methods and that stationarity of V SXS of Port and Stone, proved by Port and Stone. They have shown that the moments of the process of the tracer position are asymptotically equal to the moments of this process, so the process as if the velocity but at position 0. And these are asymptotically equal to the moments of fractional Brownian motion. Our starting point was then, of course, in all of these former results, the limit was Gaussian. And we were wondering, is it possible to obtain a limit which is non-Gaussian in this framework? So for what random fields V, velocity fields V, the limit would not be Gaussian. But this fact that in the super diffusive case where they took Gaussian, what was really important, although very non-trivial to show, is that the moments of the tracer were the same as moments of this process where the space position is fixed. We thought that, well, maybe if we can construct V, take a different V that would, again, and if we could show that the moment, the process x epsilon is behaves as a process as if this was time position 0, then but something non-Gaussian here, then we might obtain something different, because that reminded us about the construction of the Rosenblatt process. But I'll start here with fractional Brownian motion. Recall here the simple model that if one has a stationary Gaussian sequence with mean 0, and such that the covariances are of the form of certain covariances at a distance j are of a certain power, negative power of j, then if one takes If one sums up these Gaussian random variables up to nt, integer part of nt, scale appropriately, then this process converges in law to fractional Brownian motion with Hurst parameter h. I recall what a fractional Brownian motion is. And so this is the model for fractional Brownian motion. And if one takes here the similar stationary Gaussian sequence with covariances at the distance of the two variables at the distance j, again power of j, but it has to be different than in the previous model, different power, but certain power of j. Then if one takes a square, psi j square minus 1, well, this has to be a variance of, it has to be second moment of Cj, so in this case it's 1. Hermite polynomial of order 2, and sum up to nt, integer part of nt, scale, then this converges to a certain non-Gaussian process. This is called Rosenblatt process. And in fact, the one-dimensional version of this limit theorem, so one-dimensional is for t equal to 1, appeared in the work of Rosenblatt, who was looking for a non-trivial example of a stationary Gaussian sequence without strong mixing. He showed that this converges to something that is non-Gaussian, so these can't be strong mixing. And the Rosenblatt process itself was introduced later by Takpu in 1975. So what we were thinking is that perhaps if we, in this model, if we took something that would be more or less like a square of the random field that was considered by Fan Yang and Komorowski, there is a chance that we would obtain in the limits something like a Rosenblatt process. Oh, sorry, there's another slide that perhaps not all of you are familiar with Rosenblatt process, so I wrote here some of its properties. So it lives in the second Wiener chaos, so it's non-Gaussian. It has various integral representations. Here's one of them with respect to Brownian motion. It's a double integral with respect to Brownian motion. Continuous trajectory is self-similar. With index h has stationary increments, not a semi-martingale, and it is infinitely divisible. Okay, so coming back to our problem, as I said, we wanted to have something like a square of the random field considered by Fan Yang and Komorowski. But it won't be described as a square, but it will be described as a double integral with respect to a certain Gaussian noise. So W dt. So first I'll describe our random field, velocity field V. So we have complex Gaussian noise, d-dimensional. So V1, W1, WD are independent. And center, oh sorry, I forgot to write centered. They are centered and such that if you take them on test functions, then the covariance of this on two test functions is Kronecker delta. So, they are independent. Wj and Wj prime are independent, and this is the covariance. So one can think about this noise as if one takes the ordinary white noise and in time space t and k, and then take Fourier transform with respect to the space derivative. Then one ends up with something like this. So we'll be integrating with respect to this noise, and our velocity field is described by this formula. Let me explain what it all is. A, we've got a certain cutoff function A. It's continuous and compact support. Alpha smaller than 1, and so we take square root of A, AK prime, and here again K prime to the power D minus 1 plus alpha. There is the exponential part with times and powers K. Powers of k to 2 beta, k prime to 2 beta. They will, after some integration, they will, say neutralize these powers here to 2 beta. That's why I didn't mention that. Yeah? And we take a double integral with respect to this Gaussian noise. Perhaps I'll recall on the next slide what double integral means in this case. But there's not just one double integral, but we have to make our field divergence free. So we have to take certain sum of these integrals with this gamma. Gamma is similar, is the same as above, in fact, but it's taken in kk prime. So this part gamma will be responsible for making the field divergence free. Yes? Yes, thank you. Sorry. The integral, what is this double integral? Let me briefly recall that if the function that we integrate is a tensor product of two functions, then what one takes is integrate these functions with respect to the noise, each of them, and take I missed the word. Sorry? No. Yeah, in this case it's covariance, but here you take the product in dimension 2. You take the product and subtract the covariance. In general, it would be the big product. Oh. So in general, it would be big product if we were wanting to take higher order, more integrate with respect higher order integrals. And then it's extended by linearity. It's shown that that this integral only depends. It doesn't depend on the symmetrizations of the functions, and then it can be extended to symmetric functions. Symmetric, we take sk as one variable and s prime p prime as second, and so on. And then one can extend it to other functions in L square by defining it as an integral of the symmetrization. But the field defined in this way has the properties that we want. So stationary, isotropic, divergence-free, and the spectrum satisfies power law. And our main theorem is that in this case, if alpha is smaller than 1, alpha plus beta is greater than 1, and this is delta, then the processes of the tracer position converge in law. So recall this is you scale the velocity by epsilon and take larger and larger time scales with scaling by epsilon to minus 2 delta time scale. And then they converge in law to the process, which is non-Gaussian. That's what we want. Non-Gaussian and can be described as a double integral. Double integral of this form. Let me recall this. Yj was on the previous slide. Yj was the certain sum of double integrals. Yeah. So that's this is the result. So this process lives in the second chaos, has stationary increments, and is self-similar with index h, which is alpha plus 2 beta minus 1 over 2 beta. Again, we can obtain any h between 1/2 and 1. How it, let me also mention how it relates to the Rosenblatt process. Namely, if instead, if we didn't have this requirement of divergence free, which is important for our proof because we use Porton-Stone results on stationarity. But if this was simply a double integral with respect to Vj, so if we took this kernel and integrated with respect to Wj ds dk Wj ds prime dk prime, then the process one obtains in this way is the d-dimensional Rosenblatt process that d-dimensional is with independent coordinates. Each of the coordinates is an independent Rosenblatt process up to multiplicative constant. So in this way, we also obtain another characterization or another description of the Rosenblatt process that didn't see before. The proof of this proposition is, well, it is quite technical, but it uses the moment, and it uses the moment method and techniques that we also used in our paper with Bojdecki and Gorostisa that allowed the writing of the moments of such processes with respect to Feynman diagrams. I didn't have time to explain what this is. Let me, if I, perhaps I can say a few words about the proof of the main theorem. So the first step is a certain time scaling. So we write here what the h was, delta was on as in theorem, and h is also appeared already. It was more convenient for us to write this scaling that appeared, and we speeded up the time by the factor of t now t goes to infinity. So when one writes out the equation for the position of the tracer and the these terms, then it looks like this. X epsilon t is this, and we have to, in other words, we have it's good to write and multiply and subtract by t to the power 1 over 2 beta, which will be clear in a moment. So the process that we are interested in satisfies this equation. But then we look at the random field that is rescaled in this way, that is this random field that appears in this equation. And then by using the properties of how the Gaussian noise scales, one can show then that this random field has the same law as the random field Vt described here, which is actually has the same form as our V, except with only one difference, that in this cutoff function there appears a k to t minus 1 over 2 beta, and the same as beta. In V we only have this. Sorry. There should be, instead of Vj, there should be this sum with gammas. That was responsible for the divergence field, so it's that it should be sum. So, in other words, we can reformulate our problem and say satisfies this equation with this new Vt. And then it is shown that the process Vt integral 0 to t Vt are at 0, space position 0. This process converges. By this rescaling we have reduced convergence of finite dimensional distributions to convergence in a square in this case, and this is shown by the properties of the double integrals. So this is fairly easy, although needs some computation. Then one can show that our tracer, after the rescaling, the tracer process, and the process with Vt at 0, because remember this Zt was integral 0 to t Vt r of Zt divided by t to minus 1 over beta, so that this converges to 0. Well, in fact, there is a little difficulty here, namely this lemma we can show in the case alpha plus beta over 2 for the moment. We can show in the case alpha plus beta over 2 greater than 1. But we believe that it will be true in the general case, although the proof that we thought we had didn't really work. But we can prove the main theorem. We can prove the main theorem, unfortunately, not only by the moment method, but it does work. And maybe I'll skip it. Perhaps I could show you the simple case of lemma 3, how our tracer particle minus t in this process at 0, how it behaves, because one expands, right? We know that this is this, and then we've got equation for zt, the equation with Vt, so we can write this out as a gradient of Vt at a different s, and then at z at a different position u, and then Vu, because this was the derivative of ztu, right? And in this simple case, one can apply Hölder inequality, and this will be something. And then now we can see that we can use stationarity, and by stationarity over trajectories, we can reduce to calculating moments at 0, and this can be done. One can estimate Vt 0, 0. It explodes as t goes to infinity. It explodes, but the derivative here helps us, and for this part will be small, but only under this additional assumption. As I said, in the general case, we can use moment method. And there are some complicated calculations, but the main point is that we expand, and the initial terms we can compute because, again, thanks to the stationarity, we can reduce to compute some things at 0. And the remainder, we would like to use some Hölder inequality. And for this, we have to know that after taking the sufficiently many derivatives and sufficiently many integrals, that we'll get a certain power of t that is increasing. So if we expand far enough, we'll get a power of t that will kill off the other terms that were large in this after. When we apply the Hölder inequality. Okay, here for this we use some techniques for calculating these moment here we take conditional expectation. So we have to expand and take conditional expectation and then calculate the moments. And for this we use some properties of multiple integrals. In fact, we have two important ones, namely how to take conditional expectations, and for multiple integrals is easy. Conditional expectations with respect to v up to time s, right? And then one simply takes the same function f that one integrated and then cuts it to the time minus infinity s. And another ingredient, important ingredient, was that because when we expand, we have more and more products of double integrals, and we have to be able to treat them. But we can write a product of multiple integrals in terms of, okay, maybe I won't explain this, but we write it in terms of other product of multiple integrals. We write as a sum of product of double integrals. We write as a sum of multiple integrals of higher orders now, or smaller and higher. But it can be written in terms of Feynman diagrams. But sorry, I don't have time to say anything more about it. Maybe there are questions. Okay, thank you very much.
Thank you very much. We have time for comments or questions. Let me ask the first one. I understand that this delta that you obtain is greater than 1, which is the Gaussian.
It's small. I think it was smaller than 1 because in because in Gaussian case is 1, and here we need. I think it must be smaller than 1, right? Let's see.
Maybe you're right, because it's inverse.
Yes.
H is smaller than 1. Delta. I think the inverse of this.
Yes, because H certainly I have written here. Here H is a bit more. Yes.
Bigger than 1. So this requires like having a longer time interval than when compared to the case in which gives Gaussian limits. Right? So my question is, if you would take the scaling typical of the Gaussian limits, would you have converse to 0 or something?
That would be something trivial, right? It must be something trivial. Because let me think. I think it should be 0.
So it's like getting a higher order asymptotics. Would you think that using linear chaoses of higher order would give some other?
Well, I think that here there seemed to be a natural possibility of obtaining other processes, namely instead of taking double integrals there, if we take integrals of higher orders, then probably in the limit we would obtain processes that are Hermite type processes, because Rosenblatt process is the Hermite process of order K, of order 2. So in these ones, when one obtains Rosenblatt process in this simple model, here one puts a Hermite polynomial of order 2. If you put here Hermite polynomial, higher order Hermite polynomial, you obtain so-called Hermite processes. And we think that by taking fields that are triple integrals or quadruple integrals, we would obtain other Hermite processes.
Linking diagrams of higher